All right, so we're here in 129S, and down here today is session management, and then I'll demonstrate the SQL injection in the Web Security Academy. So let's pick up with that. Okay. All right. So session management, the point of this is, as we talked about before, HTTP is a stateless protocol. You send one request, you get one response, and that's it. Nothing in the protocol remembers who you are. So you have to add something outside to put it in there, and that would be to maintain your session. You have to somehow identify who you got a request from when they logged in, and record the fact that they are logged in, and then keep track of who they are later. So if you were able to defeat session management, you could move to another user's account or even to administrator. And this happened to me at DEF CON years ago. I went to DEF CON and they said, this is a dangerous network, you shouldn't use it unless you know what you're doing. And I said, I know what I'm doing. I'm using Gmail, and Gmail uses HTTPS. Therefore, I boldly used the DEF CON network, and they got in my Gmail because I didn't know it at this time. The Gmail at that time used HTTPS to log in, and then after that it downgraded to HTTP and just sent a cookie to identify which people could steal. And they had a tool they wrote called Hamster and Ferret to do that. So it was, I learned something by getting hacked at DEF CON. And when you get hacked in a certain room, the people will put you on the wall of sheep to humiliate you. So that's good for you. All right, so you need to have a state. And so Web 1.0 was the original web, like my web page, where you just view a page and it just sits there. You don't log in. You can't post anything. You know, that's basically just using a web server as a file server to just let you see static files. Then Web 2 is where you log into things like Twitter and stuff, and then you get to post things. And now you have to keep track of who people are. So even if you don't have a login session, you usually want to keep track of who people are to target ads and for things like to keep track of purchases in their shopping basket before they finalize the purchase and so on. You can downgrade HTTP only with just a 302 redirect. You redirect to, that's a good question, why? There was a belief at the time that HTTPS was too expensive, that it would cost too much server time. It wasn't until Google upgraded from HTTP to HTTPS and said it really only added like 1% of the server load that everybody accepted they could afford to go to HTTPS. But at the time, around 2010, many people thought that HTTPS would greatly slow down their servers and be expensive. Anyway, so the server's response after you log in will give you a set cookie header. It might even do this before you log in, as we'll talk about. So it'll set some kind of session token, depending on what language was used to write the website. If it was Microsoft's ASP, it'll be called something like ASP.NET Session ID. So you have this thing, it's just a bunch of random letters. And now it's stored in a cookie, so every single request your browser makes back to the same server will repeat that cookie, so that can be used to keep track of who you are. Now the problem is, if those tokens are not really random, if they can somehow be predicted, then I can guess somebody else's token, or if you handle that token unwisely so somebody can steal it, then I can steal somebody's token, and in both cases I can then impersonate that person. Now sometimes the software generates a token, but the particular website you're using is not really using it, so the way to find it is to find out which token actually identifies you, is to use something like Burp Repeater, and this is what I did with Amazon.com a few years ago. I would go to Amazon.com, log into a test account, and then I would send it to the repeater, and the original request had a lot of cookies. And then what you do is just delete the cookies, and it knows who I am. I'd open a page that recognizes who I am, like Hello Sam, and then start deleting cookies and replaying it until it forgets who I am. And then I can figure out which of these things identified me. And it was this one, xmain. I could delete everything but xmain, and it still remembered who I am. So that's a simple way to find out which token is actually being used. And the others are doing something else. They're either just useless appendixes or being used for ad targeting or for some other purpose. And I was very excited when I started doing this with Amazon years ago. I found Amazon using insecure tokens that were sent over HTTP mixed with HTTPS tokens, and I thought I'd found a real vulnerability, but I found out at that time Many ad servers used HTTP only. So you had to do that. You had to allow some HTTP content, and you had to have some HTTP content mixed with your HTTPS content to cooperate with a wide variety of advertisers. I imagine that's better now. ASP.NET. Django and Spring Boot. Well, I don't really know enough about Django and Spring Boot, but I imagine they do something similar. I know PHP does. And Java does. I think a lot of different things at different levels said all those. So all those crazy cookies are used by different parts of the system. Remember, this is something we talked about in all these lectures. When you talk to a site like Amazon, you're not talking to one server. You're talking to dozens of servers that are each contributing some small portion to that page. And all those cookies might be used by all those internal servers to record who you are in various ways. All right, so there's alternatives to these sessions. There are other techniques that have been developed. For example, HTTP basic authentication would automatically send a username and password every time a server requests it. And Digest and NTLM do it too, and they each try to scramble it in various old-fashioned ways that aren't really very secure, and they're not used that much anymore. They're mainly only used inside Windows networks. And there are sessionless state mechanisms where you don't have a session token and you don't manage the state. So the session token, like the ASP token we saw, is just a random number. Now your server has to have a database where it knows that random number and it keeps track of who you are. And that's, of course, a burden for the server. So there's an alternative way to do it, where I send all the data to the client in a big blob of data, everything I need to know about you, and then you send that back to me every time. So I do not need to maintain a database on the server. And that's these view state things. ASP calls it a view state. Java has a similar thing. And so you'll have you can make code on the server that creates an array and adds items to the array list and then sends it off as a view state from the server. So it packages all the data you want to store on the client and stores it on the client. Of course, this means you're trusting something that came from the client, but it can be signed. But you can put anything in there, booleans, strings, integers, anything you want, as much data as you want. And then, if it's not assigned, anybody with a Burp extension could hack it and alter it, and that would be bad. So you usually encrypt it or sign it. And the ASP view state uses a base64 hash and a hash made from a machine authentication code. So base64 is the data, and then it calculates a hash. And this includes has an authentication code to verify the identity of it, and it hasn't been altered. So that's pretty good. Then you can actually get a blob of data that came only from the client and trust it, and now you have saved yourself the bother of running a database on the server to keep track of the temporary information about your clients. So if these are being used on a website, you'll see a big token, more than 100 bytes long. You'll get a new token in response to every request. It'll be encrypted or signed. And if you try to submit the same item with more than one request by sending it to a repeater, you will typically have it rejected. All right. So here's another example from somebody on the web. You'll find it on my page in link 7K. This guy got a $15,000 bounty because he needed a password reset at Facebook at this time. They would email you a 6-digit code. And he would then go try to guess those 6 digits, but Facebook would rate limit you, so you couldn't guess them quickly. But he found these other websites like beta.facebook.com that were not rate limited, so he could use Burp Intruder to guess the 6-digit code. And for that, he got $15,000. Remember, I found a few of these, but nobody ever paid me anything for them. They either just didn't care or they told me somebody else found it first. Anyway, in case I haven't mentioned it, making money on bug bounties is a pretty miserable activity. You're a lot better off to get a real job because you almost always get told it's out of scope or somebody else found it first, in my experience. Anyway, all right. So here's a use case of tokens. You send somebody a token. m.facebook or /n. I can't quite see it up there. Yeah, there are other Facebook domains out there. Anyway, So you can send a token to an email address. You can put it in hidden form fields, which is going to be highly recommended later in this chapter. You can use it for one-time access, remember me, or to keep track of the status of the user. A lot of reason why you might want to use a token, but you want to make sure that all these tokens are unpredictable. You should never be able to guess or design somebody else's token, or you'll get into somebody else's account. So here's an example. A bug bounty is the way of not hiring someone full-time effectively. Well, you know, bug bounties, the original idea of bug bounties is that they would help you find vulnerabilities, and basically you would simulate the getting hacked by bad guys stuff, and it would benefit you. Even the people like Katie Mo, who are responsible for arranging a big bug bounty program, seem to have sort of get fed up with them. I think we're reaching a time when a lot of people are deciding that bug bounties turned out not to be such a great idea. It probably would be better to actually just get some trained staff, like you're saying. Actually hire some good security staff to secure your stuff would probably be better than bug bounties. Anyway, so this looks random, but it's not. 75, 73, 65, those are hexadecimal for user equals staff. So it's not random at all. It's just a hexadecimal version of readable characters. And therefore, since you have a username right there, you can just change the username to admin or something, and that might work. You know, the usual ASCII chart that you can get anywhere, man ASCII on a Linux system or Google ASCII. Here's what you often find in these structured tokens. The username, a numeric identifier, like a user ID, email address, the group or role, like administrator, and other things like an IP address or a timestamp. All these quantities might be in that blob of data. And then you encode it somehow. You can XOR it, you can base 64 it, you can just turn it into hex like the one I was showing you. So if you want to try to crack a token like that, get a token and just modify it. Send it to the repeater, change it 1 byte at a time or 1 bit at a time, and see what you can do. Burp has a feature called char-frobber that does this in an automated way. So you log in. Another thing you can do is log in several different times with different accounts and record the tokens. And if you can, register similar usernames and try to find patterns. This is how I found the Caesar cipher at Stitcher. And look for patterns or encoding or obfuscation. A series of repeating letters will give you repeating output if you're using XOR. And if you're using base 64, it'll typically end in equals or double equals. And the other thing about base 64 is it uses uppercase and lowercase letters, numbers, and just 2 punctuation marks. Well, people do every dumb thing. There's just a lot of developers that are writing something, and when they get to the encryption, they just throw something in because they don't know much, and they don't even realize it's unsafe. So a lot of what you find is incredibly silly and dumb. Just a lot of people just have no idea how to do it, and they just throw something in. Another thing that's really common, of course, is somebody just throws in something and says, well, that's temporary, and I'll fix that later. And then, of course, later doesn't come. Anyway, so try to guess the token of other users and see if you can load a page that somehow gives you somebody else's name. This is a way to see if you successfully managed to guess another person's token. So let's try a Kahoot. That should be pretty good. 7A. There it is. I remember something else to use Caesar Cipher was a Cisco training product, not from Cisco, but to use Cisco equipment called NetLab. It used Caesar Cipher, and then it added random letters to make it look long so it would look like an MD5 hash. That was pretty hilarious. Anyway, all these bad things are out there. Yep. That's the thing about security. All right. All right. So what encoding would turn that into that? All right, that's base 64 because it's got uppercase and lowercase. And another trick, by the way, is it gets longer. It takes 4 characters of base 64 to encode 3 characters of ASCII because it puts 6 bits per byte, 6 bits per character instead of 8. So that's what you get. It cannot be hex or MD5 because those would be hexadecimal and they would only have letters A through F. They wouldn't have these other letters. How about this one? That's MD5. MD5 is this long hexadecimal blob, 128 bits long. All right. How about that? That's hex encoding. You use this a lot in the exploit development class. Capital A is 41. 41, 41, 41, 41. There are the A's. And the lowercase letters are bigger numbers like 75 and 73 for users. So that's just hexadecimal, just ASCII. Yeah, that's right. If you calculate them a bit, you get used to them. MD5, you get used to seeing a lot. The others are just much longer. All right. All right, how about that one? Yep, that's XOR because the A's have turned into the wrong number, but they're all the same. So you've XORed with a single byte. All right. All right. All right. All right. Good. All right, so let's talk about things that would make your tokens predictable. And this might happen a lot. Often there are pull platforms that have a vulnerability like this. And if you have something you can download and put on your own server, then it might be easier to get a lot of test tokens to examine. So one simple thing is just sequential tokens. Here's Burp just trying a payload of 071B, 2248, 7F, and so on. It's just tried a whole bunch of different numbers here. And as you see, one of them is John Herman, one is the administrator, one is Pablina, and on it goes. So they had a simple token that was too short. So you could just try all the values until you hit other people's tokens. So if it's not that easy, if they aren't just counting up numbers you can guess trivially, there's ways that it can still be predictable. You can conceal the fact that it's just counting up. You can base it on time, or you can use some attempt to find a random number that isn't very good, where you can predict that random number. Here's a concealed sequence. These look like random things, but if you think they're base 64 and you decode them, you just get random junk. So it looks good, but it's not. If you just turn them into numbers and calculate the difference between sequential numbers, you'll see it's always the same. What this is just counting up by a constant value and keeping only the lower bits. So it's, in fact, this is a concealed sequence. It's just jumping up by certain numbers, and you can just write a little Python script that will do it. And here's the active ingredient. You just, this is the magic number, and you just multiply that. You keep adding that number, and every time it rolls over, you take away the rest, so you keep only the lower bits, and that's how you can predict these numbers. So that's a concealed sequence. When did we turn this into hex? Well, yeah, you do have to turn it into hex. So if you go back to the code here, I imported base 64 and then convert to hex here by using, yeah, this is it. This is what decoded it, B64 decode. That turned it into, yeah, that's right. Yep, that's all it is. And you could do that in CyberChef or a lot of places. Good. All right. Another thing is time dependency. Here's a token with two numbers. Now, the one on the left just keeps counting up, so that's easy to predict. But the one on the right is changing, but it's not changing randomly. Like the first digits always stay the same. It's jumping up. And if you take the difference, it's jumping up by a few hundred each time, sort of randomly. So that's a little screwy. So what you can do is try waiting 10 minutes later and getting the tokens, and you'll see the first number has gone up by 6. But the second number has jumped by 600,000, which is 600,000 milliseconds. So the second number just seems to be counting the number of seconds. So that, by the way, is not absolutely necessary for this to work. You could just stop right here and say it seems to be incrementing only by a small number, so I could still guess a token and guess the next number by not guessing too many values. But now that you've decoded the algorithm, here's your attack steps. Keep polling the server frequently, and watch when it goes, and every time you pull it, your number will go up by 1 on the left. Wait for it to go up by 2, and you know there's a number in between, and you know the second number will be between the two numbers you have. So now you just have to try a few hundred guesses to guess somebody else's token. All right. And then there's weak random number generation, which is a huge problem for computers. It's been all along. It's just hard to get a random number out of a computer. So this used a this Jetty system used a linear congruential generator, which just multiplies the previous token by a constant, adds another constant, and keeps the lower 48 bits. And what that means is it's really just another form of a concealed sequence. If you find any one value and you know the constant, you can predict all the rest. And PHP, in earlier versions, used these to try to get a random number, IP address, epoch time, which is a count of the number of seconds since January 1, 1970, or some other base count, microseconds, a token creation, and a linear congruential generator. And none of those are very good. So the vulnerability sat around for 10 years as a theoretical thing, and then Sammy Kamkar, a famous hacker, wrote an attack tool that would really hack into it. The very famous hacker, he wrote, I think, the first MySpace worm that hacked like 1 billion MySpace accounts and actually got punished for that, but he continues to write tons of hacking tools. All right. So that's how to test the quality of randomness is actually an interesting question. Here's your Gilbert about it. Your random number generator gives 999999, And is that a good random number generator or not? You don't know, right? It could give you 9 6 times in a row. That might be random. Yeah, banned from the internet for some period of time. Lawyers do that pretty often to punish you for hacking. Oh, you go to court and they put you on probation and say you cannot use the internet. Happened to a lot of people for like a certain number of years. Happened to a lot of the famous hackers. All right, so here's what you do, of course. Rather than trying to prove directly that something is random, what you do is you assume it's random, and then you apply some tests. And then you reach a point when you have proven that the tests show that it's very unlikely that this would have happened by random. That's what you do, by random chance. That's the math. Anyway, and that's what Burp can do. There's something called Burp Sequencer that can do this. You can choose something, and it will then attack it using techniques like this. I think you might only get this with the professional version. And then it will try to see what parts of the token are not random. And here the red bits were always the same or predictable. These were unpredictable. These were somewhat predictable. And of course, it's using various mathematical tricks to determine that. All right. And then there's encrypted tokens. So this is where you take meaningful content that you want to stick in there, like username and such, and then you encrypt it. Now, if you encrypt it with a secret key not known to the attacker, that sounds good. The attacker will not be able to decrypt it, but they might not need to decrypt it depending on how good your encryption is. One common mistake is electronic codebook ciphers. This is also called textbook encryption, where you take inputs of data that's your 16 bits long, or 16 bytes long, and you encrypt a block, and then you encrypt another block with the same key and another block with the same key. So this means each block is encrypted separately. Now the problem with that is if you encrypt something with patterns like this, it will still have patterns. A blob of green turns into this purple, and every other blob of green turns into the same purple, so a lot of the information is still present in the encrypted data. That's why this is not a good idea, ECB, but it's used by a lot of amateurs because it's the first thing that comes to mind. If you just implement encryption yourself, it is the simplest thing to do. Just take each block of data and encrypt it separately. So here's an example of this. If you have a token like data like this, a random number, an app, a user ID, username, time, and all that junk, and then you encrypt it 8 characters at a time, it looks meaningless, but all you have to do is break it up into blocks that contain 8 bytes. And now you can rearrange these blocks and they will still be valid decryption. So notice here I have UID equals 218. Well, if I could move another number down like this one, I could have my UID be a different number by just rearranging these blocks. So, for example, move that one down. Now your UID 992. And if you're careful and you make another user with a different length of a name, you can make it to UID 1. So you made a user named DAF1, and now the 1 rolls down here. So now I can copy that up here, and now my UID equals 1. And even if you can't decrypt any of these to know what you're doing, you can just randomly shuffle the groups of 8 bytes. There aren't that many combinations, and you might hit somebody else's account, even though you can't decrypt it. This is pretty cool. I wrote a whole project where you did this live, and I took it out of the class because I think it's better to just focus on the Web Security Academy stuff. But that's the trick. And all right, so this is why electronic codebook attacks, electronic codebook encryption is not recommended. And so the alternative that most people use is cipher block chaining. And here you have an initialization vector in addition to a key, which is just usually some random bytes. You XOR that with the plain text before you encrypt it, and then you take the output of this and use it as the IV for the next block. So each block affects the next block, and now it's much better. Now when you scramble that logo of Apple, it's really just good and random looking. Every block is totally different, so all the patterns are gone. So that's why it's highly recommended and preferred, and it's the one most people use. The problem is it has a weakness. So if we do the same thing again, have a lot of data, we encrypt it, it looks random. The problem is it's using blocks, and one block affects the next block. So if you look at the decryption process, the ciphertext starts here, you decrypt with the key and then XOR with the initialization vector, and then this ciphertext is used as the IV for the next block. So if I change 1 byte, I will completely scramble this block of plaintext, but I will only change 1 byte here of the plaintext because that's used here with an XOR. So if I'm willing to accept collateral damage of destroying 8 or 16 bytes of data, I can manipulate 1 byte at a time of the plaintext data without knowing the key. And this is the padding oracle attack that we're using in the exploit development or the encryption class. I'm not teaching this semester, but anyway, that's the point. So what this means is you can just try altering it. So if I alter it, things will happen like this. Some bytes will turn to junk, other bytes will change, so the bold byte changes. So as I change things, I'll eventually hit the UID, and now I'm getting in somebody else's account. So it's the same thing. You can modify a session token with just a long random junk, and you can set burp to, in the professional version, you can tell it to flip each bit one by one. Will ciphertext stealing be enough to fix it? It probably would, or using counter mode. Counter mode is what most people recommend these days. Use Galois counter mode is the recommended solution. Anyway, so now it won't take that long because you're flipping 1 bit at a time, so it really will not be very many requests. And the same thing happens. You change the payload a bunch of ways, and most of them will be junk, but eventually you'll hit somebody else's account, Peter Wiener and John Herman, and so on. So, well, I think there might be some of these in the Web Security Academy. I kind of think so. I'm not sure I saw these, but I think it'll be in there because the whole point, in one sense, the purpose of the Web Security Academy is to get you to try all the features in Burp. Anyway, another thing that might happen is it might use the same encryption code elsewhere in the app. And therefore, you might be able to feed in something that is under your control, like your username, and it'll encrypt it for you, and then you can feed in something else. That's the kind of thing you'll find. I did a lot of, when I did hundreds of Android app audits, I would make a username that was 32 A's, and then I would look for that being encrypted in ECB mode. I found that a lot, because you'd see it repeating in the ciphertext. Anyway, let's take a look at the 7B cahoots. A lot of stupid encryption in Android apps. Yeah, I think the mobile apps will be coming up next semester. And we'll hack a bunch of Android apps. Yeah. And maybe we won't even need an emulator. Windows 11 is supposed to support Android natively, so that might make the class easier. The problem with that class is it's very hard for students to set up a machine to use. Next semester, supposedly, we'll be back to face-to-face, and we'll have the lab again, which will be real important for that class, because in that class, more than any other, students often cannot do it on their home machine. Anyway. All right. Let's give it a shot. All right. Which token uses the same token every time the user logs in? Encrypting meaningful data is what would do it. It's actually your username or something. So every time you log in, it re-encrypts the same data. These others create pseudo-random numbers that are typically different for every session. All right, which one do you exploit by rearranging blocks of ciphertext? That's an electronic code book because each block is encrypted independently, so rearranging the blocks produces something that is still valid. All right, which one can be exploited by changing a single byte? Yeah, that's the cipher block chaining. Good. All right, which one uses one block of data to influence the encryption of the next block? That's cipher block chaining. All right. All right. It's two-time winner, and I know who that is. And another two-time winner. All right. All right, so it's just 10 minutes to 7. Let's take